What if I told you that right now, somewhere above the Japanese countryside, a 16-car train carrying over 1,000 passengers is slicing through the air at 200 miles per hour, and it will arrive at its destination within 30 seconds of the scheduled time printed on tickets purchased weeks ago? This isn't a lucky day or perfect conditions. This is Tuesday and Wednesday, and every day for the past 60 years across a rail network that has carried more than 10 billion passengers without a single fatality from train accidents. How do you engineer reliability that makes atomic clocks look casual? How do you move the population of a small city every hour while maintaining precision measured in seconds? The Shinkansen didn't just solve transportation. It redefined what humans thought was possible when steel meets obsession with perfection. The 1-minute promise. When Japanese engineers designed the Shinkansen in the early 1960s, they set what seemed like an impossible standard: average delays under 1 minute per trip. Not for slow suburban trains creeping through stations, but for bullet trains racing between cities at speeds that would terrify drivers on highways. Today, that promise still holds. Across the entire Shinkansen network, delays average 54 seconds, and that includes weather delays, mechanical issues, and the occasional passenger emergency. During peak hours on the busiest Tokaido line, up to 16 trains depart every hour in each direction. That's one train every 3.75 minutes, carrying up to 1,323 passengers each, traveling at maximum speeds of 320 kilometers per hour. The mathematics are staggering. Every day, the Tokaido line alone moves roughly 450,000 passengers, more than the population of most cities. Yet this mass movement happens with clockwork precision that makes Swiss trains look casual. Train operators carry watches calibrated to the second, and platform staff bow as trains depart exactly on schedule. But punctuality this extreme creates its own problems. When trains run every few minutes at aircraft speeds, there's zero margin for error. A single delayed train doesn't just affect its passengers, it ripples through the entire network, potentially disrupting hundreds of thousands of journeys. So how do you engineer reliability that borders on the supernatural? The answer starts with eliminating every possible source of delay. Shinkansen lines have no grade crossings, no intersections where a stuck car could halt a 200 miles per hour train. The tracks are completely separated from conventional rail, preventing slower traffic from causing bottlenecks. Even station stops are timed with military precision, exactly 50 seconds at major stations, during which cleaning crews perform their famous 7-minute turnaround ballet. Steel versus sky. Here's a puzzle that stumps transportation planners worldwide. On the Tokyo-Osaka route, commercial jets cruise at 500 miles per hour, while Shinkansen trains max out at 200 miles per hour. The plane is literally 2.5 times faster, yet the train captures 88% of travelers between these cities. How does steel consistently beat sky? The secret lies in understanding total journey time versus top speed. When you board a Shinkansen at Tokyo Station, you're already in the heart of the world's largest metropolitan area. 2 hours and 22 minutes later, you step off directly into central Osaka. No security lines, no early arrival requirements, no trudging to distant gates or waiting for baggage. Airlines, by contrast, operate from airports built far from city centers. Haneda Airport sits 30 minutes from central Tokyo by train. Once you factor in arriving early, security, boarding, taxiing, flying, landing, deplaning, and traveling from the destination airport, that 2-hour flight becomes a 4 or 5-hour journey. Suddenly, the train doesn't just compete, it wins decisively. But speed isn't the only factor. Frequency transforms convenience into dominance. Tokyo-Osaka flights might depart every hour. Shinkansen trains leave every 10 to 15 minutes during peak hours. Miss your train? Another arrives shortly. This frequency eliminates the anxiety of rigid scheduling that plagues air travel. The phenomenon reveals something profound about human behavior and urban design. We don't just travel between points on a map. We travel between the places where we actually live and work. By connecting city centers directly, high-speed rail shrinks not just physical distance, but psychological distance. Cities 500 kilometers apart feel accessible for day trips, business meetings, even weekend visits to family. Airlines understood this threat early. In the 1970s and 80s, Japan's carriers deployed enormous Boeing 747s as short-haul Airbuses between Tokyo and Osaka, cramming 500 passengers into planes designed for intercontinental routes. But even massive aircraft couldn't match the combined convenience of downtown-to-downtown service and subway-like frequency. The biomimetic breakthrough. In the early 1990s, Shinkansen engineers faced a crisis that threatened to halt progress entirely. As trains pushed toward 270 kilometers per hour, they began creating explosive sonic booms every time they exited tunnels. The compressed air pushed ahead of speeding trains would burst from tunnel mouths like cannon fire, producing ear-splitting cracks that could be heard kilometers away. Japan's mountainous geography meant tunnels weren't optional. The Tokaido line alone passes through 66 tunnels. If engineers couldn't solve the boom problem, speed increases would become impossible in a country where high-speed lines snake through densely populated valleys. The solution came from an unexpected source, a birdwatcher named Eiji Nakatsu. As head of development for the 500 series trains, Nakatsu spent his free time observing kingfishers near his home. He noticed something remarkable about how these birds hunt. Despite diving from branches into water at high speed to catch fish, kingfishers create barely a splash. The secret lay in their beak design. The kingfisher's bill transitions gradually from the bird's head to a sharp point, allowing it to part water smoothly rather than creating turbulence. Nakatsu realized this same principle could solve the tunnel boom crisis. Traditional train noses were blunt, pushing air aside abruptly and creating pressure waves. By extending and tapering the nose using the kingfisher's profile, engineers could compress air gradually rather than explosively. The 500 series debut featured a dramatic 15-meter nose, nearly a third longer than previous designs. The results exceeded all expectations. Tunnel booms vanished entirely, allowing trains to maintain high speeds through populated areas without noise violations. But the biomimetic breakthrough didn't stop there. The elongated nose also reduced overall air resistance, actually improving energy efficiency despite the added length. Each subsequent train generation pushed the concept further. The E5 series boasts a 16-meter nose, while the experimental Alpha X test train features an extraordinary 22-meter nose profile, longer than some subway cars. This isn't just aesthetic refinement. It's acoustic engineering that enables 320 kilometers per hour operation through Japan's intricate landscape without disturbing the millions who live along the routes. Modern Shinkansen noses represent one of transportation's most elegant solutions, a design borrowed from nature that simultaneously solved noise pollution, improved energy efficiency, and enabled higher speeds. Sometimes the most advanced technology draws inspiration from a bird fishing in a quiet stream. Beyond wheels, in the mountains southwest of Tokyo, something unprecedented is taking shape. Tunneling machines bore through solid rock, creating the foundation for the Chuo Shinkansen, a maglev line that will connect Tokyo and Nagoya in just 40 minutes at speeds reaching 500 kilometers per hour. This isn't simply a faster train. Magnetic levitation technology eliminates physical contact between train and track entirely. Superconducting magnets lift trains 10 centimeters above specialized guideways, propelling them forward through precisely controlled magnetic fields. Without wheels, rails, or friction, maglev trains can achieve speeds impossible with conventional technology. Yet the maglev project reveals something profound about the original Shinkansen's achievement. Despite promises of revolutionary speed, maglev construction has taken decades and cost hundreds of billions of yen. Environmental concerns about groundwater disruption and noise have sparked fierce local opposition. Technical complexity has repeatedly delayed opening from an initial 2027 target to the 2030s. Meanwhile, conventional Shinkansen technology continues advancing. The latest E5 series achieves 320 kilometers per hour, using steel wheels on steel rails. Technology that would have been recognizable to railway engineers a century ago, refined to extraordinary precision. Test trains have pushed conventional rail technology to 443 kilometers per hour, proving that steel wheels haven't reached their limits. This comparison illuminates the Shinkansen's true innovation, not revolutionary technology, but evolutionary perfection. Rather than abandoning existing rail principles, Japanese engineers refined them to previously unimaginable standards. They proved that boring steel wheels could deliver speed, frequency, reliability, and efficiency that surpassed any alternative. The maglev future may eventually arrive, but the Shinkansen's legacy lies in demonstrating that extraordinary transportation doesn't require exotic technology. It requires extraordinary execution of proven principles. 60 years later, trains that would have seemed futuristic in 1964 remain cutting edge by global standards. Perhaps that's the most remarkable achievement of all. In an era obsessed with disruption and revolutionary change, the Shinkansen succeeded through relentless refinement. It took the humble concept of steel wheels on steel rails and engineered it to perfection, creating transportation so reliable that single-minute delays make headlines. The next time you hear about transportation breakthroughs promising to revolutionize mobility, remember the Shinkansen. Sometimes the most profound innovations don't replace what came before, they perfect it. In a world of self-driving cars, hyperloop concepts, and urban air mobility, Japan's bullet trains continue doing what they've done for 60 years, moving millions of people with mathematical precision, using technology that's simultaneously ancient and impossibly advanced. That 1-minute delay I mentioned at the beginning? In Japan, it's not just a statistic, it's a promise kept, one journey at a time.